Okay, so in this video, we will be answering a few, well, not just a few. This is basically going to be my review on applications on differential equations. So there are four main applications on differential equations. From my experience, you basically make use of techniques such as variable separable and linear method. So we have growth and decomposition. We have Newton's law of cooling. We have, what else? Mixture, no? Or chemical solutions. And lastly, electric circuits. So yeah, let's answer now, no? It says here, so we have DNA. DNA deteriorates over time. So from this word, it tells you that we're dealing with deterioration. If excavations indicate only 1.2% of DNA survive after 20 million. Okay, so we have time. Well, you have to expect that you'll be listing time values as well as x values. That x value will depend on the context of the problem. Here, it is gonna be the DNA, no? DNA present. I'm not really sure what unit to correspond to DNA, but yeah, X is the DNA present at any time T. So, okay, what percent of an original sample would have been lost after 10 million years? So, let's just write here DNA as the unit. For time, we're gonna write years, but since this is million, let's simplify it, no? Let's just say million years. So we start with 0. So deterioration of DNA, it says we have to start after, just right after a dinosaur dies, no? So time 0, this is when the dinosaur dies. The next data we have 10 million. Next is 25. So when time is 0, our x value is usually written as x sub o or x sub 0, no? The next question here says we have to estimate the half-life of the dinosaur DNA. So let's write half-life here. Half-life is represented as t 1/2. So consequently, you can say that it is x sub o times 1/2 also. So this is our table, no? You need to make a table. Ideally, make one so your data is organized. You won't get confused when it comes to the application of the differential equation part, no? Okay, so it says here 1.2% of the DNA survives after 25 million years. 1.2% of what? Of what we originally started with. We convert the 1.2% in, say, mass fraction form. I don't think that's the right way. Basically, if you want to remove the percent, you divide it by 100. So that becomes 0.012. Then times x sub o. What percent of an original sample would be lost after 10 million years? This we don't know at all. Let's abbreviate this as J, no? We don't know their values. All of these. So this is a deterioration kind of problem, no? So this is what you have to remember when we're dealing with this kind of problem. Deterioration, we have a negative sign. If this problem were a growth problem, it's gonna be a plus sign. So here, dx over dt is proportional to x. Okay. We can further reorganize the equation this way, no? Then we can integrate. So this is not a simple growth problem. We have many missing values here, no? At the x column ba or row? I'm not sure. Column, I think. So time, let's start with 0. And then 25. I want to choose these two pairs specifically because both of them have x sub o. In this kind of situation, I suggest that you do that. 0.012 ln x, and then so the integral of the x over x is ln of x, no? Sorry, x sub o minus negative k times quantity, times t. Later we will substitute. So f of b minus f of a, no? For definite integrals. ln of 0.012 x sub o over x sub o equal to negative k times quantity 35 minus 0. Because you can see, x sub o can cancel. We only have one variable left, no? Doing this, we are able to find the value of k, which will be very crucial for the next step. So ln, by the way, in this part of differential equations, at least in my class, you're allowed to use a calculator. So at this point, use a calculator. So k is equal to 0.12. Wait a minute. 0.012. What is 1.2 divided by 100? 0.012. Let me just confirm if that k value is correct. Why is it? Why did I put 35? This is supposed to be 25. My bad. Divided by 25. 0.1769. Okay. Unfortunately, I was able to detect that because I already solved this before making this video. I'm not supposed to challenge myself, but this was one difficult question. Okay, so we have the k value. Let's go back to our original equation. Dx over... Let's just work with this one. Integral dx over x minus k integral d sub t. Sorry, dt. Replace k with... Well, you just substitute 1769. So, what do we do next? Let's try to make use of this pair. So, using t is equal to 10 and x is equal to j. J is what we assign to this missing value. I think that's what we have to look for, no? The first question. what percent of the original sample? Yeah. Well, this is just an instrument to the final answer. So ln of x is equal to negative 0.1769 t plus a. Oh, no, no, no. We're gonna make the integral definite. So we're not gonna put plus c or plus a constant. We start again with 0 equal to t and x sub o. And then t is equal to 10, x is equal to j. Okay? ln of x j x sub o equal to t is supposed to be 10. So 10, 0. So ln j over x sub o is equal to negative 0.1769 times 10 minus 0, which is just 10. So what's next? Let's remove the ln. So we have j over x sub o is equal to e raised to negative 1.769. What is the value of e raised to negative 1.769? Okay. So that's 0.1705. Let me try something. Let's go back here. So we can rewrite this as ln of j minus ln of x sub o. Remember your properties of logarithms. And then apply e on both sides. J minus x sub o is equal to negative, e raised to negative 1.769. Again, this is 0.1705. So from this approach, we have to assume that j is equal to 0. 1. So 1 minus x sub o is equal to 1.705. X sub o, therefore, is equal to 1 minus 0.1705, which is 0.8295. This is 82.95%. There, you got the answer. I'm not fond of this approach. I know that I think you might find it confusing. But essentially, the j here, so knowing that 82.95% is what was lost after 10 million years, what remains of it? 82.95 minus 100. So, 95. The remaining is basically 17.05% of the original. So this is what remains as of the 10 million years that went through after 10 million years. So yeah, this part is kind of controversial. Okay, so now that we were able to find our first answer, this is what, sorry, of Exabo lost after 10 million years. That's our first answer. Second, so we have to estimate the half-life. What do we do now? Zero point zero 1.1705. I'm gonna try this. There's no guarantee, but let's give it a try. So we're gonna solve this as an indefinite integral. We know the value of k, which is, sorry, this is the deterioration. So negative, don't forget the negative sign. Let's try. Let's try t equal to 0, x sub 0 equal to, well, we don't know it, so just substitute it as is. So t, this one becomes nothing, 0, no? So a is equal to ln x of 0. Will this help us? I'm not sure. What did I do? So that's already the x sub 0 value. What? No, that can't be true. Let me check my answer key. Okay, so k value is correct. We got the first one correct also. That's a given. Where is it? Okay, so apparently I did not find x sub O. I'm partially not surprised. Okay, so this has no merit to... It doesn't help our solution. Let's try that approach. But then at the same time, there's no... When integrating, there's supposed to be a plus a. You can't just leave that. Figure what I mean? Wait, let's actually try this. So we actually found what the a value is. Ln x is equal to negative k t plus a. So we're definitely not going to use the same pair. Let's try a different one. T equal to 10, x equal to 0.1705 x above. Actually, this might actually work. I'm excited. Ln 0.1705 x sub o equal to, so this one times 10 is negative 1.769 plus ln x sub o. Yes, so I think this is helpful. We were after finding k, the constant k, we find the other constant, which is a. You find that coming from integration of the equation that we started with. And then right now, you just have to solve for x sub o. 0.1705 x sub o is equal to a raised to negative 1.769 I think this is how you do it. Let me think. So yes, you are given you are allowed to use a calculator in the exam, but you still have to show your solution. That is what has been mentioned to me. So as much as I wanted to, here I'd already want to shift solve, but to be safe, you show your solution. 0.01705 minus 1. Okay. A raised to negative 1.769 x sub o is equal to let's see. Wait a minute. Okay, something's wrong. Let me try using my other calculator. 1705 times x equal to negative 1.769 plus ln of x. Wait. I want to resolve. Before applying E, uh, 0.1705 x sub o, we transpose this to the left side I don't like this. Yeah, some things. Yeah. We were not able to find Exabo. Let's go back here. In some way, uh, although what we have right now isn't wrong. Let's try LNJ over Exapo, the one we initially started out with earlier. So when we apply Euler's number, so we have J over X sub O, E raised to negative 1.769. So recall, X sub O means the initial amount, the amount that we originally started with, and J is the amount after 10 million years. So we expect it to be lower. So let's assume X sub O is 1, no? E raised to negative 1.769 is 0.1705. So J itself is 0.1705 off the original amount. Therefore, so coming from 100% minus 17.05%, we get what? 17.05, 82.95%. So that is what's lost after 10 years. I think that holds the answer to our question. So we were able to find this answer on the assumption that x sub o is 1. Or let's say 100%. 100. Therefore, this is... Let's just move this here. So on the basis of 100, this is 17.05. This is 1.2. This is, well, coming from 100, it's the half of 100 is 50. Okay, I think that is a safe assumption. Let's see. So coming from there, let's not use this for a while. Let's start with what we already have. Dx over x integral negative k integral dt. Let's use two pairs. Let's say 0 to 10 years, coming from 100 to 17.05. Let's see what happens. Oh wait, no. We already have all the values. In this case, we can find k. Let's actually do it. Let's see if we're gonna find the same k value. I think that's one way to test. ln 17.05 over 100 equal to negative k times 10. Let's see what k is. I think in theory it should be the same. So yes, it is the same. Yeah, it is the same. So that's a good sign, no? We're getting somewhere. Only, let's do the same. We can choose any of these pairs with this, because it's the half-life that we're trying to find. So t 1/2, and then our x value corresponding is 50. Let's solve. So 100 to 50, k is 0.1769, t 1/2, and then 0. ln 50 over 100 is equal to negative 0.1769 times t 1/2. Solve. That's gonna be ln 1 over 2 over negative 0.1769. Solve. .92. Remember the unit? Million years. I think that is the answer. There you go. 3.92 million years. Okay, nice. You were able to answer it in one page. That is an achievement. And the solution isn't that long. Initially, it took me like two pages to answer. Let's now move on to the next question. So, a variation on population problem is when population size has an inhibitory effect on the growth of the population. So, population size is going to be our x value. Yeah, affirmed. Then, dx over dt is equal to k times quantity a minus x times x. Okay, so we're given an equation. This kind of model can be extended to many situations called self-limiting problems. Gossip. This is a gossip kind of question. Okay, so we start with, one person in small town, population of 200. Let's have time and x. X unit is person, one person, for example. T is what? Days. No? We start with 1 day. 0 days. One person proceeds to spread a rumor. So one person already knows about that information on the 0th day. Population 200. If the rate at which the spread is proportional. Okay, so it says here, the rate at which a rumor spreads is proportional to the number of people who know the rumor. So that's going to be X. This is a growth problem. So we're going to expect that the equation is positive K. No? Find the expression for the number of people who know about the rumor after T days. So in other words, we express X as a function of T, or time. What's the next question? How many people will have heard the rumor? So given T is equal to 2, what is X? So how many people? That's our X value. Given time is 2 days. And then third question, will the entire town eventually hear the rumor? So the question for that is not numerical. We need it coming from A and B. So we'll find out later. Okay, so what else? T, aside from 0, we have 2 days. 1 is our X sub 0. Uh, 50 people know about the rumor after 1 day. Okay. T is equal to 1. 50 is the X. The second day, this is what we have to look for. How many people will have heard the rumor after 2 days? Okay. I think this is sufficient. We have 2 pairs. Fortunately, this is the scenario. Unlike a while ago, it's much more difficult to comprehend the problem if it were not that straightforward. No? Okay. So we acknowledge that A and K are constants here in this equation. Dx, we just organize it in such a way. Okay, dx over x is equal to K times quantity A minus x dt. Let's also move A minus x to the other side. I'm not sure if we can solve this as a linear dE. I think that's harder. Let's try to make this variable separable. So u is gonna be xa minus x squared. Du is equal to, so this cannot be ln x. A minus 2x dx. Yeah, we cannot. How do we solve this then? If u substitution cannot work, we are going to solve this using partial fraction decomposition, or PFD. So how do we solve using PFD? So let's rewrite this fraction. So 1 times quantity A minus x. This is equal to A over x plus B over A minus x. multiply all sides by x quantity a minus x. You get 1 equal to a times a minus x plus b times x. So we can solve for a and b using two methods, although I think method 1 will suffice. If you remember your partial fraction decomposition from calculus 2, this is exactly what you have to do in differential equations. So method 1, let's say x is equal to 0. 1 equal to a times quantity a. Wait, we have another constant though. What do we do with that constant? The a constant. That's actually messing me up. Let me check my answer key. Ah. So a is the 200. I didn't know that. How are you supposed to know that? Where is that said? Population of 200. Where does it say that a is 200? Although I think you already know that if you're familiar with the equation. I think this is specific. It's not a random equation. It's something that you remember in the context of a population problem. So a is 200 according to the problem. So that gives us perspective. This is 200 minus x. So either way, you cannot use u substitution. Okay, so x is 0, so this will be 0. A times 200. A, therefore, is equal to 1 over 200. Okay. And then let x equal to 200. 1 equal to a times 200 minus 200 is 0. Plus b times 200. Same thing. B is also equal to 1 over 200. Substitute back. So 1 over x times quantity 200 minus x is equal to 1 over 200 over x plus 1 over 200 over 200 minus x. Okay. So the other side will be, wait, we're gonna use this now. The other side is k dt. Don't forget the dx here. We have two pairs. Let's simplify this equation first. 1 over 200x plus 1 over 200 times 200 minus x. So integrate. U is 200x. du is 200 dx. Okay. So 1 over 200 ln x, ln u. Okay, next. U is 200 times 200 minus x. Let's simplify this already. Negative 200 dx. Other side, k, t. By the way, let's already put our pairs. Again, this is this is x, this is time. So in the x, we have 0 to 1. In the x values, we have 1 to 50. So 50, 1, 1, 0. Okay. So substitute 200 ln 200 times 50. Oh boy, this is gonna be a long solution. 40,000 minus 200 times 50. So that's f of b. F of a, it's the same thing, only... Okay, this is actually pretty long. Bruh. Only we replace it by 1. At the other side, so we have k times 1 minus 0. So just simply k. We'll deal with that later. In the meantime, simplify. 1 over 200 ln 200 times 50 minus 1 over 200 ln 40,000. Okay, for this part, negative 5.49 times 10 raised to negative 3. How about the other side? Okay, so negative 5.49 times 10 raised to negative 3 plus 0.02647 is equal to k. Simplify. Okay, so we were able to find our k value. Let's now use either one of these two pairs, and given t is equal to 2, we find x. Again, this is time, this is x. Where is our general solution? This one. So 0.02098. Wait. The updated one. I'm looking for the updated one. This. What happened? Bruh. This one rather. paste. Okay, so we just replace the lower and upper limits. For time, it's coming from 1 to 2. For the x, it's coming from 50 to what we don't know. Let's abbreviate it as j, variable j. So j. Okay. This is gonna be a long solution. So this time, just replace this with... Oh wait, no. Let me think. Why is my solution so long? I don't remember it being this long. Anyways, so this is gonna be j. This is gonna be 50. At the right side, so 0.02098 times quantity 2 minus 1. This one can be simplified as it's the same thing as earlier. Negative 5.49 times 10 raised to negative 3. If you want to show the solution, something that we're supposed to do, we multiply all sides by 200. So we have ln 200j minus ln 40,000 minus 200j equal to this times 200, which is negative 1.0986 equal, sorry. Let me just verify my solution earlier. I might be having a problem with the signs. Here's a negative 3 minus, sorry, plus 0.02647. Yeah, nothing's wrong. Carry on. So this itself is a negative, no? We have a minus. So this is gonna be plus. Okay, so 0.02098. Times 200. 0.02098 times 200 is equal to 4.196. Okay. Let's narrow it down further. We can simplify LNs this way. 40,000. Let's factor out 200. 200 minus j. Okay. And then the other side, transpose this to the right side. What do we get? 1.0986. We have 3.0974. When we apply Euler's number on both sides, this by the way cancels. We have j over 200 minus j equal to e raised to 3.0974. Multiply both sides by 200 minus j. What we end up with is Well, distributive property, 200e raised to 3.0974 minus j e 3.0974 equal to j plus j e raised to 3.0974 is equal to 200 e raised to 3.0974. Factor out j. Writing fatigue. Let me just duplicate that. Okay. J is equal to this divided by this. Okay, calculate. 200e raised to 3.09741 plus e raised to 3.0974 191.36. But since we are dealing with people, there can't be a person represented as a decimal value, no? One person is one person. That's plain common sense. So round it off to the nearest whole number. This is what we get. 191 people at t equal to 2 days. So this is the calculated amount of people that would have heard the rumor after 2 days. Okay? So that's how you solve this problem. It says here, 191. So our solution is correct. Okay, so those are just a few problems on growth and decomposition. Let's now move on to Newton's law of cooling. This is a different kind of difficulty. Let's start first with the easiest question. A thermometer reading 18 degrees Fahrenheit is brought into a room. Okay, when it comes to Newton's law of cooling, what is different? It's still the same. We have, well, no, it's not the same as our previously used formula. So this is for growth and decomposition, no? This one. If it's we're talking about growth, we put a positive sign. If we talk about decomposition or deterioration or decay, then it's a negative sign on kx, no? When it comes to Newton's law of cooling, the formula is going to be dt, capital T as in temperature, over dt, small t as in time, and then Tm, kt minus Tm. Let me see if I still remember it correctly. I think that's the formula. Newton's law of cooling. Precisely, this is the formula. Okay, a thermometer reading. So we're now going to organize the information that we have, also in the form of a table. When it comes to mixture, you don't form a table anymore. You draw what the mixture is like. So that will be for later. Right now, let's focus on Newton's law of cooling. Thermometer reading 18 degrees Fahrenheit is brought into a room. We're gonna have time also. Here it is in terms of what? Minutes. Our x here, let x equal to temperature reading in Fahrenheit, degrees Fahrenheit, at any time t. Okay, So, thermometer reading of 18 degrees Fahrenheit is brought into a room. So, upon bringing it to the room, time is 0 minutes. The temperature of the room, it's actually T sub m, the one that is written in the formula. So, right now we are given its value. Later on, we will find problems wherein we have to look for T sub m, but in replacement, we have to look for, we're given something that we're looking for right now. So, yeah, some problems are the other way around, if you think about it. Okay, 1 minute later, the reading is 31 degrees Fahrenheit. 1 minute later, so T is 1. Determine the temperature reading. Okay, required. You have to find X as a function of time and find the temperature reading. Sorry, X if T is 5 minutes. So after the thermometer is first brought into the room. This is an easy question. You have to prepare yourself for what's to come later. Okay, so let's reformat this formula. dt over t minus t sub m equal to k dt. We are given two pairs, so we don't have to do something crazy yet. Let's just input the values. So 0 to 1, and then 18 to 31. In this case, we would be looking for t. And also, what you have to know is, in this equation, you have to assume tm as a constant. So, if we were going to integrate this, u is t minus t sub m, no? du, therefore, is equal to dt. Tm is gonna be 0 because it's a constant. Therefore, this could be done by u substitution, integrated by u substitution, ln t. Then 31, 18 equal to k t 10. Okay. ln 31 over 18. Sorry. We're not gonna use x, we're gonna use t. T as in the temperature. K 1 minus 0. K is equal to this one itself. Let's see. 31 over 18 is 0.5436. Okay. Let's now substitute that to the original formula. So K is 0.5436 times quantity T minus T sub m. Yeah. Since we're treating T sub m as a constant and we are given its value, we can just substitute. Okay? So, again, what are we looking at? Find the temperature reading 5 minutes after. Okay, so given that T is 5, we're looking for its corresponding X value. Okay, so we're gonna make use of this. Sorry, where is the dt? Wait, no. We need to reorganize it again. So dt over t minus 70 is equal to 0.5436 dt. Then we put the integral sign. So we can choose any of these two pairs. They're characterized by having both t and x values. We can choose any of them. We pair it with this. So I want to try 1 and 31. So coming from minute 1 to minute 5, and we come from 31 to, well, the value that we're looking for. Let's make it j, no? Okay, so ln t j 31 0.5436 times t 51. Okay, ln j over 31 is equal to 0.5436 times 5 minus 1, which is 4. Put e on both sides. We have j over 31 is equal to e raised to 4 times 0.5436. That's 2.1744. Multiply both sides by 31. So we have 272.70. What's the unit? Degrees Fahrenheit. Hold up. Why is it suddenly so big? Wait, something's wrong. uh, let's see. Ah. Oh, wait, no. Never mind. Zero 0.5436 times 4, 2.1744. Why is it wrong? So we can solve this another way. Let's try 0 and 18. Let's try this pair. 0 and then 18. Two 2.718. It's the same thing. 70 degrees Fahrenheit. Temperature reading as a function of time. Time. Let's try something. We start again with dt over t minus t sub m equal to k dt. This is ln t equal to k t plus a So t is equal to e raised to k, which is 0.5436 times t plus e raised to a. This is supposedly the answer, no, to expressing x as a function of time. I'm gonna try something. So this is time, this is x. Given 18 and our time is 0, okay, so e raised to a is equal to 18. Wait, sorry. 18 is equal to e raised to 1. So e raised to 0, wait, e raised to 0 is 1. Yeah, 1. So e raised to a is 17. If we want to ln both sides, to actually find what A is ln of 17. 2.833. Sorry, 2.83. That would suffice. But yes, e raised to A is 17, if ever we need it later on. So to be more specific, t is equal to e raised to negative 5436t plus 17. Did we get it right? Okay, so it's not shown. From there, I think we can already find. So given T is equal to 5, what is the temperature? Let's see. I'm excited. Negative 0.5436 times 5 plus 17 is... Ouch. Why is it 17.07? Is that the answer? No. What? What is going on? Let's check the answer key. The solution is very simple. Where did we get it wrong? K is... okay, so we already got it wrong with the K value. What happened? 103118 doesn't seem to be wrong. T minus 70. Headache. So this is supposed to be ln u, no? So T minus T sub m. I only wrote T. That's what got it wrong. Restart. Everything here is wrong. Okay, so ln Tm is 70. Just put this in the calculator. Okay, so that is our K value. Let's substitute it to the original equation. dt over dt equal to K times quantity T minus Tm, which is 70. I think you can solve this two ways. Let's try method 1 or way 1. So we are going to integrate as a definite integral. Zero to 5 minutes, and then 18 to j. ln t minus 70 j 18 negative 0.2877 t 5 0 ln j minus 70 over 18 minus 70 equal to 5 minus 0 is just 5. apply ln on both, e on both sides. Five times 0.2877 is 1.4385 negative. J minus 70 is equal to 18 minus 70 is negative 52 over e raised to 1.4385, and then just add this to the other side. Transpose negative becomes positive. Calculate. .4385 plus 70, 57.66 degrees Fahrenheit. So we got the answer, no? 57.66. So that is the first method. Another way to solve it is making use of the indefinite integral. So let's try the second way. Oops. Bruh. Give me a minute. Okay, way 2. We start with this, no? dt over t minus tm integral negative 0.2877 dt. And then don't forget the integral. This is going to be ln t minus tm equal to negative 0.2877 t plus a. So again, tm is 70. And then let's find from the table. We want to find a using any of these two complete pairs. Let's try using t equal to 1, using t equal to 1 and x equal to 31. Sorry, I keep saying x. This is supposed to be t. Ln 31 minus 70 equal to negative 0.2877 times 1, which is just the same thing, equal to plus a. So simplify. Ln 31 minus 70 plus 0.2877. Why is it math error? Wait, I think the calculator isn't accepting, it doesn't accept negative values. What is 31 minus 70? Negative 39. We can rewrite this as negative ln 1 over 39. Okay. So plus 0.2877 equal to a. Input this in the calculator. Okay, so a is 3.95. Given that, let's update our general solution, which is this. Just replace a with an actual value. And now let's use t equal to 5. in order to find its corresponding temperature, which we represented as J. So ln T minus 70 negative 0.2877 times 5 plus 3.95. This is a property, okay. I'm multiplying it by e raised to 3.95. Two three seven three e raised to 3.95 82.32. What's the unit? Degrees Fahrenheit. Okay, why is the answer different? Oh no. Let me see if I did the manual solving correctly. Let's shift solve. Let's shift solve this one. Okay, nothing's wrong. Maybe it's the A value. What happened? Ay, nako. What if, just to be safe, we use T equal to 0, temperature equal to 18? Ideally, in theory, we're supposed to arrive at the same A value. Let's see. 18 minus 70. This one's gonna be 0, so just equal to A. Okay, that's gonna be easy. 18 minus 70 is negative 52. Rewrite this as negative... we don't have to try using a different set. I think I see what's wrong. Oops. So coming from ln negative 39, if we make this as 1 over 39, the negative sign is eradicated. Okay, I think that was what we were supposed to do. Negative 3.38, therefore is our A. With 7 times 5 minus 3.38. Let's remove remove this. So E raised to negative 4.8185. 70 plus this one. Let's see what we get. is it a different answer? What? I think it really does have something to do with this. What did I do in my previous solution? Okay, so I didn't use this method. What I did was this, and we had no problem. I think if you encounter this, it's an indication that you have to stop solving because you're gonna get the wrong answer. This is said to be not a real number. The technique that I was taught was, for example, if you have negative ln of x, you can rewrite this as ln 1 over x. But if the negative were inside the natural log, this is a different discussion. No? So you have to stop solving from here on. So yeah, we got the answer anyways. We tried another way, but it's a good thing that we were able to try, because now we're aware that if ever we encounter this again, we know what to do. There has to be another way, which is this. This is 57.66. Okay. Steel ball placed at time equal to 0, maintained at temperature 30 degrees Celsius. Minutes. This is temperature. Sorry. This is temperature in degrees Celsius. Heat flow. So at time equal to 0, steel ball is 30 degrees Celsius. At the end of 3 minutes, temperature of the ball is reduced to 70. After 15 minutes, temperature of the ball becomes 42. Okay, find the initial temperature. So 30 is not the temperature of, not the initial temperature, or X sub O. That tells us that 30 degrees Celsius is our room temperature, I think, which is maintained at the temperature of, yeah, maintained. I think that's the key word. Okay, so this is a Newton's law of cooling problem. So dt over kT minus Tm, which is 30. Let's find K using these two pairs. So 3 to 15. Sorry. We don't apply the integral sign yet. We have to rewrite T minus 30 equal to K dt. Okay. 3, 15, 70, 42. ln T minus 30, 42, 70, K T 15, 3. ln 42 minus 30 over 70 minus 30. Alright. And then K times 15 minus 3, which is 12. K is equal to ln 12 over 40 divided by 12. Solve. 42 minus 12, ln 12, 40, 12. Okay, 0.1003. This is our K value. Looks weird, no? But that's usually what you expect for a K value. Now, let's replace our new equation. We now know the K value. 1003 times quantity 3t rather minus 30. Rearrange t minus 30. Let's use one of either of these two complete pairs. I want to use 15 and 42. So 15, 42, x sub o, 0. We're gonna look for x sub 0. We know the time, which is 0. So ln, let's bring it down. No? It's kind of crowded over there. Okay, ln t minus 30, 42 x sub o equal to negative 0.1003 t 15 0. ln 42 minus 30 is 12 over x sub 0 minus 30 equal to negative, copy k, 15 minus 0 is just 15. Apply E on both sides. E raised to, what is 15 times 0.1003? Negative 1.5045. Okay, 12 is equal to A raised to negative 1.5045 times x sub o minus 30. Distributive property. Okay. Calculate. One point 5045. So x sub o is 84.02. Makes sense because as you can see, the trend is the temperature degrees Celsius is becoming smaller, no? And yes, it says here 84. So this answer is correct. Our solution is correct. I want to solve this in another way using indefinite integral, like the one earlier. Let's see if it works. If you want to skip to the next problem, then go ahead. We just want to make sure that I can solve in at least more than one way if possible. It really tells you that it really helps you become more confident when you see a problem like this. So in case one method doesn't work, not all hope is lost because you have another idea. Okay, we want to express this in terms of t. Wait. Sorry. Yeah, let's just keep going. T plus e raised to a. Let's use one of the two pairs. I want to try 15 and 42. 42 is the t. 15 is the small t. Let's solve for e raised to a. 42 minus 30 is 12. Minus e 0.1003 times 15 equal to e raised to a. .78. So if you want to apply ln on both sides, a is equal to ln 11.78. What is that? 2.47. So what now? We go back to the original equation. Ln t minus 30 equal to negative 0.1003 t plus a. Actually, let's just settle with this one. E raised to a is 11.78. Okay. We are given T equal to 0. We have to look for the initial temperature of the steel ball. So given, using T equal to 0, so 30 plus 11.78, 41.78, plus E, this one, times 0, E raised to 0 is equal to 1. So this is 42.78. Did we get the same? No. What happened? It's like this is just half of this. I wonder what happened. $2.47. Okay, that's it. I tried to see if it was solvable using this method. Ignore. This was already enough. Okay, next. The body of a murderer was discovered at 7 p.m. Okay, so we're gonna articulate the table in this way. So we have time, another time, our usual column. This is in terms of what? We have hours. In this kind of question, I suggest we use minutes. As you can see, the answer is 8:29. So it's at least it's not in terms of seconds, no? That's much more difficult. X is what? The temperature of the body in what? Degrees Fahrenheit. Recall the equation. The body of a murderer was discovered at 7 p.m. Next time is 11:30. At 11:30, the temperature was measured. Sorry, rather taken. After 1 hour. 1 hour after 11:30, that's 12:30. This has got to be AM already. 93.4. And he noted the room temperature was constant at 70. Okay, so Tm is equal to 70. Use Newton's law of cooling, estimate time of death. Time of death. Assuming the victim's normal body temperature was 98.6. Was 7 p.m. the time zero? No, because it says here it was discovered. The body was discovered at 7 p.m. So we don't know the time when he died. Normal body temperature is 98.6. So if you think about the trend here, when you die, of course your temperature becomes lower, no? Your organs start to fail, that kind of sort. So it gives you the idea that this one is your initial temperature at time zero. So we have one pair. Let's say this is x. This is x plus 60. Because one hour is 60 minutes. Okay. This is gonna be 70, no? We want to find k, but we don't we don't have two pairs. That's the problem. So what do we do? Let's make use of these two pairs. I want this as j for uniformity. That's my favorite variable. I want to use it as a representation for something that's missing. Right now it's not the final answer, but it's missing. So how do we do that? Organize the equation. Temperature is 94.6. We go to 93.4. For the time, we start with J and then J plus 60. If you noticed so far, whenever we try to subtract here, we don't end up with a negative. So if ever you see your value to be like this, something's wrong. Okay, so J is eliminated. This is 60k in the right side. If we simplify what is in the left side, we have 23.4 and then 24.6. Okay. Calculate. Okay, negative 8.35. Sorry, 34 times 10 raised to negative 4. Oh my gosh. What is this number? Okay. Replace back to our original equation. Alright, we were able to find k. And then I wanna choose this and this. It's either this and this or this and this. Okay, so time, we start with 0, then J, and then 98.6 to 94.6. Five. Is this 5? Oh no, J. Okay. So ln 94.6 minus 70 over 98.6 minus 70 is equal to J minus 0 is just J. Okay, calculate. 94.6 minus 70. Whoops. J is equal to 180.65. Okay, this is in minutes. So J plus 60 is equal to 240.65 minutes. Now, 64, 65, 65. This one is 240.65. Okay, so we now know our unknown values. 7 p.m. the body was discovered. When was the time of death? So, do you think that the time of death is the same as the time when the body was discovered? It could be, but there is no, in this case, there is no evidence to point that out. So, what do we do? (11:30 p.m.) So 11:30 p.m. that was using the J value, 180.65 minutes. Let's say that's 181. Let's approximate it as 181 minutes. Convert that to hours. That is 3 hours and 1 minute. Is that right? Okay. So 3 hours ago, 11:30, 10:30, 9:30, 8:30. Sorry, 8. 1, 2, 3. 3 hours ago was 8:30 p.m. You account for the 1 minute, so that becomes 8:29 p.m. So using this, using what we have, we assume that at T0, the temperature of the body was 98.6. That was the time of death. What corresponds to it? We started with 11:30 p.m. Minus the 3 hours and 1 minute, we arrived at the time of death, coming from 180.65 to 0. You see the logic? That's why the time of death is 8:29 p.m. So, yeah, 8:29. The body was discovered at 7 p.m. If we want to know the time, 7 to 8 is 1 hour and then 29 minutes. This is negative 1 hour. 1 hour is 60, 60, 29. 1 hour, 60, 29. Negative 89 minutes ago. So when the body was discovered minus 89 minutes, by time 0, 8:29, the person died already. Do we know? Can we find the temperature during this time? I think we can. I don't know. But that's not being asked anymore. We'll just leave this as blank. Okay? You were able to answer the question. I'll end the video here. It's getting too long. We have a lot more questions to answer.